Hello and welcome back to math class. Today, systems of linear equations. And what this topic is about is solving linear systems of equations when there's more than two equations and two unknowns. In grade 10, in early high school, we learned about how to solve two equations and two unknowns by a couple of methods called substitution and elimination. But suppose there's three equations in three unknowns, or seven equations in seven unknowns. You can see that an organized approach is going to be needed. And this is an introduction to an organized approach to systems of linear equations. First of all, some definitions. Linear. These expressions are linear because it's a multiple of x. It's a multiple of y. Oh, sure, it's root 13 times z. It's a multiple of z. A multiple of x combined with a multiple of y. This would be a linear combination. These are linear expressions, as opposed to nonlinear expressions, which are cos of x. It's a nonlinear expression. Log of y. 2 over x when x is in the denominator, or x squared when x is squared. Or an exponential expression, or another type of logarithmic expression, ln x. These are nonlinear expressions. So today we'll focus on systems of linear equations. Systems of equations is when there's two or more equations that are in two or more variables. And a solution to a system is a set of values. It's a set of values for the variables that satisfies each equation in the system simultaneously. Number of solutions. Well, if it's a system of linear equations, there's only a few possibilities. You can have zero solutions, so no solutions at all. You can have exactly one solution, one set of values that satisfies, or you can have infinitely many lists of values that satisfies all the equations. So there's either none, there's one, or there's infinitely many. You can't have 2 or 7 solutions to the system. Consistent versus inconsistent. Well, what do these words mean? A consistent system is a system that has one or more solutions. So if there's a solution, then the system is called consistent. But if there's no solution, then it's called inconsistent. Equivalent systems. Well, equivalent systems of equations are two systems that have the same solution. So if a couple of systems have got the same exact solution, then they're equivalent. Okay. Introduction. Elementary operations used to create equivalent systems. Well, these are operations that we can do on all the equations. So we line the equations up so that the x's are over the x's and the y's are over the y's and the z's are over the z's and the equal signs are over the equal signs and the constant terms are over the constant terms. And then we can do these operations on the system. We can multiply an equation through by a non-zero constant. Now, this was done in grade 10. When you did elimination. We can multiply an equation through by a constant. You can interchange a pair of equations, so you could put the middle one first, for example. You could put the first one last. So you could interchange any pair of equations. Just they can swap places. Kind of intuitive. I mean, that's the way you think it would be, of course. And another operation that you can do is you can add a multiple of one equation to a second equation to replace that second equation. So we could take an equation and add. add a multiple of a different equation to it. And this was done in grade 10 when we would draw a line doing our elimination and add up some equations or subtract. We would draw a line and add, or draw a line and subtract. These are called the elementary row operations, by the way. Okay, let's go through an example of grade 10, except we'll do it this organized way. It's a kind of like grade 10, but it's a intro to a new method, an organized method. We're going to use those elementary operations to solve this system of equations like we did in grade 10. Step 1 is we're going to interchange, because that was one of our options. We can interchange two equations to make the top left coefficient a 1. So we're going to swap these two equations in their location so that the top left coefficient here is the number 1. And I see a number 1 here, so if I just swap these two, I've put a 1 up there. And that's what it looks like now. So on the top left, I made a 1 happen. Now, if I were to graph these two equations, this is what the two graphs look like. Notice the solution is 4, 3. Solving by graphing, the solution is 4, 3. This is the first equivalent system. It's equivalent to the original in a trivial sort of way. Moving on. Step 2. We're going to replace the second equation by itself, minus 3 times the first equation. And we're going to do this to make the subsequent coefficient a 0. See this 3 here? We want this 3 to be a 0. So we built a 1, and now we're going to make a 0 by replacing this equation with itself, subtract 3 times the first equation. So that second equation, well, let's take a look. It's 3x minus 3 times 1x, which is 0x. It's 2y minus 3 times 3y, so it's 2y minus 9y, so it's minus 7y. And then it's 18 minus 3 times 13, so 18 minus 39, which is minus 21. And then step 3, we'll divide this second equation through by negative 7. Because that's another thing you can do. It's one of the operations. I said multiply through, but dividing is like multiplying by a fraction. So we can divide through by negative 7. And now it looks like this. And I've indicated what I did. I took equation 3 and divided by negative 7 to get this equation. And then when you graph these two, this is the second equivalent system that I've shown it. Of course, the solution is still 4, 3, because that's what an equivalent system is. It's got the same solution to it. Now, since the new equation, this equation right here, since the new second equation states pretty clearly here that y equals 3, because this is 0x. So y equals 3. Sub this value back into the first equation and solve for x. So we can just take this equation and do substitution, actually. Plug it in right there. We've got 9 and 13 minus 9, which is 4. And now we can graph these two, and we've got the final equivalent system. So what can you take away from all this? We did operations, we built a 1 in the top left, and we built zeros beneath it. That's how we get started on this. Okay, let's do this with 3 equations and 3 unknowns. Solve the system of equations using the elementary row operations. And here it is, a system of equations, 3 of them. The goal of the elementary operations is illustrated in the following diagram. We want to make a row of ones happen here, right there. We want a row of ones. To do that, we're going to build this one first in the top left corner, and then we're going to build the zeros beneath it. Then we're going to build this next one in this diagonal, and we're going to build zeros beneath it, and so on. And if there was 7 equations and 7 unknowns, the method would be the same. We can dispense with the variables in the system. We don't have to say 5x, y, and z, as long as we understand that the first one's x, the second one's y, and the third one's z, and then the number on the end is what it's equal to. So we can dispense with the variables, and we can just write our system like this. And this is our original system. We can check 5 minus 2 minus 7, 19. 5 minus 2 minus 7, 19, and so on. It's the same system, the original system, and we're going to build a 1 here. Well, we can do that by replacing these 2 rows. So that's what I've done. I replaced those 2 rows. Now we need to build zeros here and here, because that's the order you have to do it in. Otherwise, when you're doing a step, you'll mess up the previous steps. So I need zeros at the 5 here and 0 at the 3. And this is our plan. We're going to take row 2 and subtract 5 times row 1. And that'll build a 0 here. And we're going to take row 3 and we'll subtract 3 times row 1. And we'll have it look like we want it to. Now this is easy to make a mistake. You copy across the first one, copy it, and then you have to think 5 minus 5 times that. Negative 2 minus 5 times that, so that'll be plus 5. Negative 7 minus 5 times 1, that's negative 12. 19 minus 5 times 8, so it's 19 minus 40. And then row 3 minus 3 times row 1, so 3 minus 3 times that, 0. 4 minus 3 times that, so that's 4 plus 3, 7. 1 minus 3 times 1, minus 2. 1 minus 3 times 8, so 1 minus 24 is minus 23. And we've built our 1, 0, 0. Now this is where it becomes quite easy to make an error, and you don't want to do that. So let's move on, just carrying this forward. Our next task is to make a 1 happen here. Make a 1 happen without messing up the 1, 0, 0 that we worked so hard to create. So we need a 1 here. And I can see that if I divide through by 3, I'll have a 1. So I'll take row 2 and divide through by 3. Very simple. Copy the other 2 rows. And now I've got a 1 here. And my next task is to turn this into a 0. And our plan will be, take this row 3 and subtract 7 times row 2, because that won't mess up this. So 7 minus 7 times this will be our 0 that we need here. We need a 0. So row 3 minus 7 times row 2. Everything else copied. So copy row 1, copy row 2. 0 minus 7 times 0. Boom. 7 minus 7 times 1, 0. Negative 2 minus 7 times, so that's plus 28, minus 2 plus 28, 26. Negative 23 minus 7 times minus 7, so minus 23 plus 49, 26. Okay, so we've got our 1, 0. All we need to do is turn this into a 1, and we've got it. Copying forward. And we'll divide that last through by 26. And we've created our row of 1s here. And everything below that row of 1s is a 0. Now, there's our row of 1s. Now we can put the variables back. We could have it wasn't necessary to get rid of the variables, but it just reduces the writing and the work. Put the variables back. And now we can start to solve this. If you look at the last row, this says z equals 1. So we start at the bottom. So x, y, z, but z equals 1. There it is. Now we'll take that and we'll plug it right in there and look at row 2. Now if z was 1, then this would be minus 4, add 4 over there, and we have y equals minus 3. So we're building it here. And we'll take these two and we'll sub them into the top one. So we start at the bottom and we build a solution upwards. So let's see, z is 1 and y is minus 3. So this is a positive 3. Drag it, make it subtract. That'll be 5. Subtract that 1, which is z, to make that 4. And so x will be 4. A system of linear equations.